Welcome to Recitation 0, Part B of Introduction to Deep Learning. My name is Sarvesh, and in this part of the recitation, I'm going to introduce you to NumPy, Python's de facto standard library for numerical and scientific computing. So in this course, and more generally in machine learning and deep learning, we'll be dealing with large volumes of numerical data, typically in the form of matrices and vectors. We'll be implementing various mathematical and linear algebraic transformations on these matrices and vectors, like matrix vector multiplication, for instance. Now, to implement matrix vector multiplication, given a matrix and a vector, you might begin by looping over the entries of the matrix and basically operating at the level of the individual numbers. But as you'll see in this recitation, a better approach would be to vectorize your code, that is, to use an API like the one NumPy provides, to express your operation at the level of matrices and vectors directly whenever appropriate. As we will see, vectorized code can be much more concise and hence less bug prone than nested for loops, but it can also be much faster because you'd be relying on NumPy's low-level efficient implementation for the numerical computation rather than using Python for loops for that purpose. Now let's begin with a simple example we're going to compute. Wx plus b for matrix W and vectors x and b. We will first have a look at a naive implementation in Python, which we will then vectorize using the NumPy API. So for the naive implementation that uses nested for loops, our vectors will be Python lists or matrix, and our matrix will be composed of nested lists, as you can see here. So W is a 3 by 3 matrix. So this is the first row, this is the second, and this is the third. X and B are initialized, as you can see here. We will also create a zeroed output Y, and now to compute the matrix vector product, we simply loop over the rows of the matrix and then loop over the entries in each row. So we have a two-level nested for loop here, and then we just multiply and add. As for the vector addition, we loop over entries in the output Y and add to every entry the corresponding entry from the vector B. And we get the desired output. But now let's have a first look at NumPy. We will vectorize the above example using the NumPy API. First, we import the library as NP, which is a standard practice. We then create our first NumPy arrays. W is a 3 by 3 matrix, which we initialize from essentially the same matrix W that we had using nested Python lists. X is a 1D vector, again initialized from a Python list, and B is initialized from NumPy array creation API. So it's a vector with 3 ones. Now for the actual computation, the matrix vector product is simply expressed using W dot X, which returns this vector, and vector addition is as simple as using the overloaded plus operator. Now let's note something here. NumPy vectors are essentially just lists of numbers. As such, they are not really row vectors or column vectors per se. Each vector works as either. If you really need a row or a column vector, you can construct a 1 by n or an n by 1 matrix respectively. Most of NumPy's code, if not all of it, really operates on n-dimensional arrays. So this can be a vector in 1 dimension, a matrix in 2 dimension, or really any n-dimensional tensor. So here we'll create and fill tensor T of dimensions 2 by 3 by 4 with random floating point numbers between 0 and 1, following a uniform distribution. Indexing works as you'd expect. So this gives us the first entry along the first axis, and T, which is this matrix, this 3 by 4 matrix, we can inspect its shape and the data type of the entries. In order to allow vectorization effectively, NumPy arrays have fixed uniform shapes like we had in this case, and have a fixed data type for the entries. So this can be a 64-bit float or a 32-bit integer, etc. Here we create a matrix X which is full of this value and has dimensions 4 by 3. The data type is specified to be a 32-bit integer. Again, we inspect the shape and the data type, and they are as expected. To compute a matrix multiplication, we use the same overloaded operator dot, and we get the output of W times X. Clearly, if we had X being full of zeros, so as an array of zeros of the same shape as X expressed in this form, we would expect the matrix product Wx to be all zeros, and clearly indeed, this matrix product is equal to a 3 by 3 matrix of all zeros. This function np.array_equal checks whether the output of w.x2 and np.zeros of which is a 3 cross 3 matrix of all zeros are actually equal. Now let's discuss basic element-wise operations in NumPy. This is where you start noticing more and more capabilities of the NumPy API. So we create this vector y, which has entries from 0 to 9 inclusive. That's the same thing as creating the NumPy array and initializing it with this Python range. So we can print both, and you can see that they are the same. So checking for equality, you might be tempted to write this kind of code, and indeed it works. But what it did was it gave us an array of 10 true values. So what really is happening here was that NumPy applied the equality operator element by element, and it figured out that every pair of corresponding elements in Y and in this array are equal. So this is going to be the basis for the next few examples. NumPy simply applies the operation element by element or elementwise, and it does so efficiently. This adds a 1 to all values in Y. This multiplies each row by 10. This adds 1 to each value in Y and then squares them. Now this is a little different. Here we are adding every value in Y to the corresponding value and the other vector which is also Y. So this is similar to doubling the values and or multiplying them by 2. As you see the trend from here, we're computing the square and then taking the square root. So we're getting Y back, except that the values here have been casted to floating point numbers. We also have the other convenient math functions like minimum, maximum, standard deviation, and sum of the products. Feel free to check the references for further functions that you're going to find useful. The links are provided at the end of the notebook. Now we'll discuss indexing NumPy arrays. Let's execute this line which saves some array into a file. Now we can load a tensor T from the file and inspect its shape. So this is one other way of obtaining and initializing NumPy arrays. It is probably the most useful to start working. So you might have a dataset and it's saved in a file, and that's how we load it. Now, as we saw above, you can simply access an element in the array like with access to like access on Python list, and this gives us this matrix. We can also access a specific numerical entry, a scalar, by specifying its position. So it's going to be 16. This is a more efficient syntax for accessing NumPy arrays, that is, in terms of behavior, equivalent to this one, except that this one has to return this array first, which involves a copy operation, and then extract this array and then return the scalar here that we're directly indexing. Python style slicing also works as expected. So if you wanted to focus on this matrix, take only these two rows and then extract these two subcolumns. This would do it. And lastly, we can do some kind of conditional indexing where we extract specific entries from the tensor or from the n-dimensional array. So what this essentially does is that t mod 10 equal to 0 provides us with the Boolean values of each element in T if where the element might be 0. So as we can see here from the original T matrix, the locations of true are coinciding with the locations of 0. When we use this as the index element of with T, we get only the values of T which only the locations where T mod 10 in the matrix T are equal to 0. Now let's discuss a quick example that uses what we saw in terms of indexing and what we saw in terms of multi-dimensional arrays. Let's create W, a matrix of dimensions 4 by 4 that has entries between 0 and 9 inclusive. Again, you know the above operations generalize to higher dimensional array. So we can do these element-wise exponentiation and division. Now let's create an array called mask, which is filled with ones, has the same shape as W2, except that we want to set the second row to 0. So this is going to use something that's called broadcasting, which we will discuss later in the recitation. But intuitively, it's just setting the second row to all zeros. Now if we compute the element-wise product of W and the mask, you can expect all these rows to stay the same and the second row to be 0, which is exactly what you get relative to this. We have seen element-wise comparisons before, so this is true exactly for the entries that are bigger than 5. So let's say we want to clip the values at 5, so that all values are either smaller than 5 or equal to 5. One way to do so would be to index into the positions that are bigger than 5 and set them to 5. And you notice that all the values now are at most 5. And it's the same thing as using the minimum function with the arguments 5 in NumPy, which would match element-wise with our W3. The next topic we'll discuss is computation along axis. So again, we can create this random matrix. We've seen the sum before of all entries. We can also compute the sum row by row, so we can add up all the rows. You can also add up all the columns by specifying the axis to be 1. We can find the maximum along columns, and you will also find the position of the maximum argument in every column. So the maximum here is at position 1. The maximum here is at position 2. And in the second row, it's at position 1. And in the third row, it's at position 2 again. So you get the argmax to be 2, 1, 2. Next is combining arrays. We're going to discuss two NumPy operations, stacking and concatenation. Let's create three vectors A, B, and C, which are of 5 elements each, filled with 1, 2, and 3 respectively. Say we want to stack A, B, and C next to one another as columns of a matrix. NumPy provides the stack function, which takes an axis argument that specifies the axis. That is, if we want to stack them along the row or along the column. If we index, we get one of the input arrays that we provided. So if we stack A, B, and C along the first axis, the second axis, which is axis 1, this is the output. If we index axis 1, we get in this case the vector B, which is the second column here. Now say we want to apply a simple transformation to be twice and then concatenate the output so that we get a wider matrix. That's what the concatenate function does. You're probably So here we are actually adding 100 to B and 200 to B and concatenating both the matrices B plus 100 and B plus 200 one next to the other. So this is this part of the new matrix is B plus 100 and this is B plus 200. You're probably familiar with the transpose operation from linear algebra. You can simply use the matrix B. So if you say B dot uppercase T, that transposes your matrix and it behaves exactly as expected. Notice that the shape is transposed. But there is also the reshape functionality in NumPy, which keeps the data in its original row major-like order, but allows you to access it and use it under a new shape. So here we are reshaping B. which was 5 by 3 matrix, so that it looks like a 3 by 5 matrix. And you notice that the original order is kept the same, but the new shape is 3 by 5. So essentially, transposing and reshaping do not behave the same. Next is broadcasting, which is another concept in NumPy that enables elegant vectorization of code. Broadcasting is basically the way in NumPy allows operations to occur between arrays that do not have strictly comparable shapes, but where the smaller array, which is the one with the smaller number of dimensions, or where some have dimension 1, can be sort of stretched to allow the operation that you would intuitively expect to actually occur. Let's take two matrices A and B initialized with of random numbers between with shapes 8 cross 4 and 4 cross 3. And you take the matrix product A dot B, and this is the output. Let's take an array B of a vector of size 3. Taking the dot product of A and B and adding that with B essentially broadcasts B into each row of A dot B. We have already actually seen an example of broadcasting where we added a scalar. It was the value 1 to a vector, and the result was another vector where every entry was increased by 1 as you probably expected. There are a few examples below. Please go through carefully and to understand the way broadcasting works in NumPy and the conditions for it to be allowed. Now we will need to deal with external data files, either as input or output from NumPy programs. So these examples here below essentially describe saving and loading a single NumPy array as well as saving and loading dictionary of NumPy arrays. Now coming to PyTorch. PyTorch is similar to NumPy in a way that it manages computations, but has a strong GPU support. You can build a machine learning algorithm even with NumPy, but creating a deep neural network is getting exponentially harder. NumPy is designed for fast computations and not machine learning. It is usually used for machine learning together with a machine learning package. Similarly to NumPy, PyTorch also has a C backing, so they are both much faster than native Python libraries. NumPy could be GPU accelerated with some extra code, but it does not have the strong GPU support that PyTorch or TensorFlow does. PyTorch was specifically tailored for GPU functionality in Python. Now, to create a PyTorch tensor, first let's import torch, which is the basic package that allows us to perform operations on tensors. Now to create a PyTorch tensor, similar to the vector, to the matrix W that we created initially, we use torch.tensor and specify the list that we want to be converted to the tensor, and along with that we can also specify the data type of each value in the tensor. Here I've specified torch.int. You can specify multiple other data types. You can see what are the different data types that you can specify in this link here. As you see, now W is now a tensor of type int32. Now to convert between a tensor and a NumPy matrix or an array, it's very simple, and we have W array is w.numpy, where W is our tensor that we just created, and W tensor is dot struct tensor W array. So essentially, if you see the array and the tensor, here you get a NumPy array of int32 data type, and this is the tensor, same as the array with the data type as torch.int32. These are a bunch of useful references you'll be probably finding useful. So this was a brief introduction to some core NumPy and PyTorch functionalities for introduction to deep learning. If you have any questions, as always, please feel free to post on the course page or on Piazza, and definitely try to go through the examples and snippets of code provided in this notebook. Thank you very much.